Here's a problem I'd like you to try. A box experiences a net force that changes with position according to this graph. If its mass is 2 kilograms and it starts from rest, find the velocity of the box at 1, 2, 3, 4, 5, 6, and 7 meters. Go ahead and pause the video, give that a try, and then we'll work through the solution. Since work is area under the force versus distance curve, then we can just simply look at the area under the curve for each of these time intervals. So for time interval 1, the area under the curve, 2 Newton meters, or 2 joules. So that's the work done on the particle by our force. And we know that the work is equal to the change in kinetic energy. The work is going to be 1/2 mv final squared minus 1/2 mv initial squared. Remember, the delta sign always means final minus initial. This is the final kinetic energy minus the initial kinetic energy. And we know the particle starts out at rest. The delta K is just the final kinetic energy. And that has to equal 2 joules. And if the mass is 2, then V final is equal to the square root of 2 meters per second. It starts out at 0, x equals 1 meter. The particle is moving at the square root of 2 meters per second. Let's look to see what happens at x equals 2 meters. We can do it two ways. We can go right from the start, x equals 0 to x equals 2, and our starting velocity is 0, and find our ending velocity. Or we can look at just this segment. We know the velocity at x equals 1, and we can take a difference there in kinetic energies. So the work between x equals 1 and x equals 2 is going to be equal to 2 joules. 2 newtons times 1 meter, the area there. Work is delta K. That's the final minus the initial kinetic energy. And the final is at x equals 2. The initial is at x equals 1. And we know this from the previous case, that is the square root of 2. 1/2 times the mass times v at x equals 2 squared minus 1/2 times the mass times the square root of 2 squared has to equal 2 joules. And now our velocity is going to be 2. Let's take a look at the next situation. We're going this time from x equals 2 to x equals 3. We need to find that area. I'm going to break that up into the bottom half and the top triangle. So that's going to be 1/2 for the triangle and 1 for the square. 1 plus 1/2, 1.5 joules of work is done between x equals 2 and x equals 3 on our object. So the work done is the change in kinetic energy. I'm going to multiply through by 2, plug in 2 for the mass, minus the mass. V2 is 2, so we square that. The square root of 11/2 meters per second for the velocity at 3. Okay, now see if you can go on and get the velocity at 4. The work is going to be 1/2 of a joule for that section between 3 and 4. So we take the work is equal to change in kinetic energy, 11/2. The mass is 2, so 1/2 times 2 cancels out. V4 squared, the mass is 2, and the work done has to be 1/2. So I get the square root of 6 meters per second for the velocity at 4. Now see what happens at 5. Now what we're interested in is the area of that triangle. And the area of that triangle is negative 1/2. Because it's below the x-axis, that is negative area. So negative 1/2 joule. So the work done is going to be the kinetic energy at 5 minus the kinetic energy at 4, and that's going to be negative 1/2. M is 2, and V4 was the square root of 6, so this is 11/2. And let's take a look at what we got at 3. At x equals 3, we got the velocity was the square root of 11/2. So let's think about this for a minute. It went from x equals 3 to x equals 4, and plus 1/2 joules of work was done on the object. So it sped up a little bit, going from x equals 3 to x equals 4. Then from x equals 4 to x equals 5, negative 1/2 joule of work was done on our object. So it slowed down by a little bit, and it ended up back at the same speed it was at x equals 3. We did positive work 1/2 joule, sped it up a little bit. Then we did negative work 1/2 joule, slowed it down by the same amount, and so we're back to where we were at x equals 3. What do you think the speed is going to be at x equals 6? I'm guessing the speed at x equals 6 is going to be the same as the speed at x equals 2. All that yellow area did positive work, increasing the speed going from 2 to 4, and all the green area here is doing negative work, same exact amount, but in the negative direction. Same exact amount, but negative, slowing the particle back down. So let's just go ahead and see what we get. Going from 5 to 6, negative 3/2 of a joule. So what do we end up with? Work is 1/2 mv6 squared minus 1/2 mv5 squared, and that all has to be negative 3/2 of a joule. M is 2. V5 was the square root of 11/2. We're squaring it. We got 11/2. That's 4. V6 is equal to 2 meters per second. Let's go back and see what we had at V2. Two meters per second. So we're back at the same speed. Now what's going to happen, we're going to slow down, going from 6 to 7. We're going to slow down by the same amount that we sped up, going from 1 to 2. So I'm expecting my velocity to be the same at x equals 7 as it was at x equals 1, because we did some positive work between x equals 1 and x equals 2, and we did some negative work between x equals 6 and x equals 7. And the work done in that area between 6 and 7 is negative 2. M is 2. And I think that's what we had for V1. Yes. V1 was the square root of 2. So you can see from our graph, if we had gone one more, if we had gone to V8, if this leveled out, we'd be back at rest. The particle would be back at rest. The idea here, work is the area under that curve. Force versus displacement curve. You find the area, and you use work as change in kinetic energy. Fairly simple. The tricky part was that when you're below the x-axis, it's negative work, negative area, negative work. And when you're doing negative work on your object, you're slowing it down. When you're doing positive work, you're speeding it up.